Here we have Leonard, who has just lost his finals basketball game, where he has been working so hard for.
Are you alright, son?
Losing sucks.
It does. But did you know each human has their own limits in life? Sometimes we just can't reach something despite working hard for it.
That's sad, Father.
It is. But do you want me to distract you from your loss?
Please do.
Funny how in mathematics, there are also limits.
It does? Please, tell me about it.
It's basically the same as what it means. It's something you want to achieve but can never be obtained.
Who taught you that, Father?
I think it was Professor Dexter de la Cruz and Professor John Rive de Nosta. A limit simply means the value you are approaching to. For us to get the limits, it needs to approach from the left hand and right hand, and it has to have the same value for it to be considered to exist. See this hole here? This is the value we are approaching. The notation for a limit is look like this. This can be read as the limit f of x as x is approaches to c equals to L, while the left hand is like this. The limit of f of x as x approaches from the left. See this negative exponent here? While the right hand, the limit of f of x as x approaches from the right has a positive exponent.
Those were the days.
Flashback.
For you to understand, let us have an example first. So we are looking for the limit of 3x plus 2 as x is approaches to 1. Let's just find the left-hand limit first. First, we need to find the value of x that is closer to or less than you see, which is 1 over here. Since we need 5 values of x, we will use the following 0, 0.5, 0.9, 0.99, and 0.999. Let us substitute first the value of our 0 to our function, which is 3x plus 2. 3 are x equal to 0 plus 2. 3 times 0 is 0 plus 2, which is our answer is 2. So, this is our f of x. Then proceed with another x function. 3 times 0.5 is 1.5 plus 2, 3.5. And next, 0.9. Now 3 times 0.9 7 plus 2. So again, 4.7. So the next function. So now next 0.9 and no 0.99. Times 0.9, no, 0.99 is equal to 2.97 plus 2. Convert again to 4.97. And next again, 4.99 plus 2. 4.99. Then the final answer, which is 4.997. system. As we can see here, the value of our x is approaching to 1 as we have a here on our C. And the value of our f of x is approaching to 5. Our limit 3x plus 2 as x approaches 1 from the left side is equivalent to 5.
Now, the right hand limit. We can get the value of the right hand limit using the same process as the left hand. Just that the value of your x must be greater than your c, which is 1. Let us use the following value. Let's say 2, 1.5, 1.1, 1.01, and 1.001. Now, let's substitute. 3x plus 2 will become 3 times 2 plus 2 is equals to 8. 3 times 1.5 plus 2 is 6.5. 3 times 1.1 plus 2 is equals to 5.3. 3 times 1.01 plus 2 is equals to 5.03. And 3 times 1.001 plus 2 is equals to 5.003. We can see that the right hand limit also approaches to 5. So now we can say that the limit of 3x plus 2 as x approaches to 1 from the right is equals to 5. Now the limit exists. Now let us graph. This is the left hand and this is the right hand, and they are approaching to 5. The plot in 5 needs to be a whole as it is only approaching 5 and it's not the value of the function. So we can say that if the graph as a whole, it means the limit exists. If the value of the left and right hand is not the same, the limit doesn't exist. Also, if the graph has a gap or break, the limit does not exist.
I think Professor Daniel Cabrillos told us about the asymptotes. And my classmates Anya Pabulaay taught me about limits at infinity.
Flashback.
In limit, we also have a asymptote. If the value of a function f of x approaches a real number f as x increases or decreases without a bound, then f has horizontal asymptote. At y equals to L, a function has a vertical asymptote. At x equals to c if one of the following conditions are satisfied. Let us have an example. Here you can see that the asymptotes come from the right and towards infinity. And let's have another one. Here you can see that asymptotes come from the left going towards negative infinity. If the value of a function f of x approach a real number L as x increase or decrease without a bound, then f has a horizontal asymptote at y equals to L. A non-constant function has a horizontal asymptote at y equals to L if one of the following are satisfied. Let's have an example. Here you can see that a asymptotes approach 4, going to the right infinity. And let's have another one. Here you can see that asymptotes approach negative 3 and going to the left infinity.
Limit also have infinity. Let's look at this. It states here that if the limit of 1 over x raised to r as x approaches to 0 from the right equals to positive infinity. Let us have an example. Limit of 1 over x raised to 9 as x approaches to 0 from the right equals to positive infinity. Another limit in infinity is this. Limit of 1 over x raised to r as x approaches to 0 from the left equals positive infinity if r is even, and negative infinity if r is odd. Let us have an example. Limit of 1 over x raised to 14 as x approaches to 0 from the left equals positive infinity. Another, limit of 1 over x raised to 13 as x approaches to 0 from the left equals negative infinity. In Theorem 1, it states here that if the limit of 1 over x raised to r as x approaches to positive infinity is equals to 0. Here in Theorem 2, it states here that if the limit of 1 over x raised to r as x approaches to negative infinity is equals to 0. Let's have an example. Limit of x over x squared as x approaches to positive infinity. Let us solve. First, we have to divide the numerator and the denominator with the variable and the denominator with the highest degree. Here we have x squared. So divide the numerator and the denominator with x squared. 6 divided by x squared is equal to 0. X squared divided by x squared is equal to 1. 0 over 1 is equal to 0. Another limit of 6x raised to 4 minus 3x squared minus 4 over 2x squared plus 3x plus 3 as x approaches to negative infinity. So, divide each term of the numerator and the denominator with the variable with the highest degree in the denominator. We have x squared, so x raised to 4 divided by x squared is 6x squared. 3x squared divided by x squared is 3. 4 divided by x squared is 0. 2x squared divided by x squared is 2. 3x divided by x squared is 0. 3 divided by x squared is 0. Now, simplify. We are left with 6x squared minus 3 over 2. Simplify further. 6x squared divided by 2 is 3x squared. 3 divided by 2 is 3 over 2. We are left with 3x squared minus 3 over 2. Now, substitute the negative infinity to x. Negative infinity squared is positive infinity. Times 3 is positive infinity. Minus 3 over 2 is positive infinity.
It seems fun, Father. Can you tell me more?
Shall we talk about the evaluating limits? And if I remember correctly, it was Professor Cyril and I who tackled it for us.
Flashback.
So there are different ways of evaluating limits. So we have here Theorem 1.1, which states that for any real number c, limit x as x approaches to c is equal to c. We have here an example. Limit x as x approaches to 5 equals 5. We have here next Theorem 1.2, which states that for any constant k and real number c, limit k as x approaches to c is equal to k. We have here an example. Limit 7 as x approaches to 1 equals 7. Theorem 1.3 states that suppose limit f of x as x approaches to c and limit g of x as x approaches to c both exist and let k be any constant, then the following rules apply. So the first rule that we have in Theorem 1.3 is what's that multiple law, which states that the limit k and f of x as x approaches to c equals k limit f of x as x approaches to c. We have here an example. Limit 2x squared as x approaches to 3. The first step that we have to do is that we have to put 2 outside, as 2 is the value of our k. Then leave the f of x inside the limit. After doing that, we have to substitute the value of our c to our x's. Like we have here. 3 has been substituted to x. 2 times 3 squared, simplify. 2 times 9, which then will become 18. The second rule that we have in Theorem 1.3 is sum and difference. Here states that the limit of f of x plus or minus g of x as x approaches to c equals limit f of x as x approaches to c plus or minus limit g of x as x approaches to c. We have here an example. Limit 7x plus 2 as x approaches to The first thing that we have to do is that we have to separate the terms by adding the limit term. So it will become like this. Limit 7x as x approaches to 2 plus limit 2 as x approaches to 2. Now let us apply the constant multiple law. Put the 7 outside. 7 limit x as x approaches to 2 plus limit 2 as x approaches to 2. Now substitute. 7 times 2 as we substituted the 2 to the x plus 2. Simplify. 7 times 2 is 14 plus 2 equals 16. So the third rule in our theorem 1.3 is the product law that states that the limit f of x times g of x as x approaches c equals limit f of x as x approaches to c times limit g of x as x approaches to c. You have an example. Limit 2x plus 1 times x squared as x approaches to 4. Separate the terms by adding a limit. It will become like this. Limit 2x plus 1 as x approaches to 4 times limit x squared as x approaches to 4. You can apply here the constant multiple law and it will become like this. 2 limit x plus 1 as x approaches to 4 times limit x squared as x approaches to 4. Substitute. 2 times 4 plus 1 times 4 squared. Simplify. It will become 9 times 16 and equals to 144. So the fourth rule that we have in theorem 1.3 is called quotient law, which states that the limit f of x over g of x is as x approaches to c equals limit f of x as x approaches to c over limit g of x as x approaches c, as long as limit g of x as x approaches to c is not equal to 0. So we have here an example. Limit 3x squared plus x plus 1 over x plus 2 as x approaches 1. We'll have first to separate the following terms by adding limit. So, limit 3x squared as x approaches to 1 plus limit x as x approaches to 1 plus limit 1 as x approaches to 1 over limit x as x approaches to 1 plus limit 2 as x approaches to 1. Apply constant law to this term. It will become like this. And after that, all we have to do is substitute. 3 times 1 squared plus 1 over 1 plus 2. Simplify. It will become 3 plus 1 plus 1 over 3. Add. It will equal to 5 over 3. We are finally done with theorem 1.3. Now let us proceed to theorem 1.4, which states that the limit of n root of f of x as x approaches to c equals n root of limit f of x as x approaches c equals n root of limit. We have an example. Limit square root of 4x plus 5 as x approaches to 5. Separate the terms. It will become this. Square root of limit 4x as x approaches 5 plus limit 5 as x approaches 5. Apply the constant multiple law. It will become like this. Square root of 4 limit x as x approaches 5 plus limit 5 as x approaches 5. Substitute. It will become like this. Square root of 4 times 5 plus 5. Square root of 20 plus 5 will become like this. Square root of 25 is 5.
It seems really cool. What else?
Oh, there's calculating limits too. Professor Desiree Apellido shared it with us.
Flashback.
To calculate limits, we can use the substitution, factoring, and rationalizing. So let's use the substitution first, and then we have our example here. Limit x squared plus 4 over x cubed plus 3x plus 6 as x approaches 2. And then we have to substitute the x to our function. So f of 2 equals 2 squared plus 4 over 2 cubed plus 3 times 2 plus 6. And then 2 squared is 4 plus 4 over 8 plus 6 plus 6 equals to 8 over 20. But we can still simplify it to its lowest term, so divide it by 4. And then we have our answer, which is 2 over 5. And now, let us move on to factoring. We have an example here. Limit x squared minus x minus 6 over x squared minus 2x minus 8 as x approaches 5. So, we have to factor out the function. We have x plus 2 times x minus 3 as a factor of x squared minus x minus 6, and then x plus 2 times x minus 4 as a factor of x squared minus 2x minus 8. And then cancel out the common factor, which is x plus 1. Then simplify x minus 3 over x minus 4, and then substitute the x to our factor. 5 minus 3 over 5 minus 4 is equal to 2 over 1 or 2. Now, rationalizing. Here, we'll make use of conjugate. Conjugate is when we change the sign in the middle of the two terms, just like what we have here. Let us solve this function. First, multiply the conjugate to the numerator and denominator, and then cancel out by terms. And then we're left with this and substitute the c to the x. Simplify further by rationalizing the denominator. And here we have air and
I think that is enough for now. We have a long time ahead to learn all this stuff. But Father, I want you to continue. Continue? Huh? I just remember this stuff. We also have continually discussed by Professor Salam Salam.
Flashback.
In limits, there is something called continuity. In order to achieve this, the following must be satisfied. F of c is defined. Limits exist, and limit is equal to f of c. Let us find out if this function is continuous or not. First, let us check if f of c is defined. Substitute 0 to the function is equals 0 squared plus 2 times 0 plus 1. And simplify. So f of 0 is equals to 1. Now let us check if the limit exists. Limit f of x is equals to x squared plus 2x plus 1 as x approaches 0. Now let us substitute the 0 to the function. 0 squared plus 2 times 0 plus 1 is equals to 1. Now, check if the limit and f of c is equal. Limit f of x is equal to f of 0. Since both has the same value, it is continuous.
Miss, what happens if the following aren't satisfied?
Well, that is called a discontinuity, Mr. Ariel, but that will be tackled in our next class.
Continue, Father.
Alright. We love IPT this time.
IPT.
Yes, Intermediate Value Theory. Tackled by Professor Stephanie Mahipos.
Flashback.
Intermediate value theorems states that if a function f of x is continuous on a closed interval a and b, and f of a is not equal to f of b, then for any value w between f of a and f of b, there exists at least one value c in the open interval a and b such that c equals
W. Alright, let's take a look at this problem. We're given a function f of x is equal to x into y, where as to explore what happens the interval 1 and 5. So first thing is to evaluate the function in the given endpoints. Evaluate the function to 1 and 5. Simply substitute 1 and 5 in the function. F of 1 equals 2 times 1 minus 5 equals negative 3. F of 5 equals 2 times 5 minus 5 equals 5. As you can see, F of A is not equal to F of A. These values, negative 3 and 5, will use to get the value of W. W is between the negative 3 and 5. So let us pick a value between negative 3 and 5. Let's say we will use 2. So now we will get the value of C since we know that f of C is equal to W. Substitute to f of C. Before doing that, we must know the value of C be between 1 and 5. F of 2 equals 2x minus 5 transpose 5. 2 plus 5 equals 2x divided by 2, and we are left with x equals 7 over 2 or 3.5. Now let us graph the following. F of A is equals 1 and negative 3, and here is f of A. F of B is equals 5 and 5, and here is f of B. F of C is equals to 2 and 3.5, and here is f of C.
Wow, those were the days I miss university. I miss it too much.
Do you, Father? Tell me more about it.
Alright. You really love math, huh?
Well, the apple doesn't fall from the tree, doesn't it?
Leonard, who was sad earlier because of his finals basketball game resulting in a defeat, is now so absorbed in his father's stories and has caused his emotions to a complete 180 degrees, that whatever sad feelings he bore earlier suddenly turned into motivation. After all, if there is ice cream to make us happy, well, it was math for Leonard. Weird, isn't it? As the son listens to his father's tale and lessons, he has grown to be more curious about math a little too much, that he ended up being a university math teacher.
Alright, class. My discussion for the day is about derivatives. This is easy, class, as long as you listen to me. First, we get to know about slope of the second line and a tangent line. A second line is simply called a secant. This is a line passing through 2 points of a curve. M sec, or the slope of the second line, is x sub 0 and x sub 1 equals to f of x sub 1 minus f of x sub 0 over x sub 1 minus x sub 0. Now, let us have an example. F of x is equals to x squared minus 3. Yes?
Can we teach me about derivatives?
Sure, let's go to the library.
Let us have an example. F of x equals x squared minus 3, where x sub 0 is 0 and your x sub 1 is 1. First, we need to find the value of f of x sub 0 and f of x sub 1. All we need to do is evaluate the function using the x sub 0 and x sub 1 value. We will have f of 0 equals 0 squared minus 3 equals negative 3, so our f of x sub 0 is negative 3, then it will be 0 and negative 3. While f of 1 equals 1 squared minus 3 equals negative 2, our f of x sub 1 is negative 2, so it will be 1 and negative 2. Now, substitute it to the formula. Slope of the line, or m sec, is equals to negative 2 minus negative 3 over 1 minus 0 is equals to negative 2 plus 3 over 1. equals to 1 over 1 or 1.
Now, let's talk about tangent.
A straight line is tangent to a given curve f of x at point x sub 0. If the line passes through the point of x sub 0, f of x sub 0 on the curve and has slope. It is called a tangent line, and x sub 0 is the point of tangency. The formula of the tangent is divided by formula is slope of the tangent line equals limit of f of x sub 0 plus delta x minus f of x sub 0 over delta x as x approaches to 0, where delta x is not equal to 0. The slope of tangent line is also the definition of derivative. The derivative of a function f at the point of x sub 0 is defined as f prime of x sub 0 equals limit of f of x sub 0 plus delta x minus f of x sub 0 over delta x as x approaches to 0, where delta x is not equal to 0. Let us have an example. F of x equals x squared plus 2x plus 3. F of prime of 1 equals f of 1 plus delta x minus f of 1 over delta x. First, let us substitute. Second, simply factor out. After that, cancel out like terms. Lastly, substitute 0 to the value of x. Then, simplify equals to 4.
It would have been really cool if all of this was true, right, Leonard?
Thank you, sir.
Oh, you're sleeping again?
Ano gramo tinamat? NBA ka pa? Tanawa score mo diho? 1 ka lang.
To the function, let us substitute let us solve.
Bascal. As x approaches to 2. 540.
Diba kung sila...
From the left,
Where give
Interval.
So now let us
let's sing this one fun, brother.
Tulong.
Values to the x. I mean to the function.
Miss, what happens if the following aren't satisfied?
A real number n.
Okay, let's go.